imagine stepping back in time to a world where figuring things out wasn't so much about careful experiments, but more about, old philosophy and kind of mystical ideas.
Right.
A time when people actually thought fire was like a basic element just escaping from things when they burned.
Hard to picture now.
It's totally. We're talking about chemistry before it really became, chemistry as we know it.
Yeah.
So today we're doing a deep dive into the life and, honestly, the groundbreaking work of Antoine-Laurent Lavoisier. He's often called the father of modern chemistry.
A title he definitely earned.
And you're going to find out how this one man, just through meticulous measurement and really sharp thinking, completely changed how we understand matter. He laid the foundations for the science you rely on every single day.
But there's also a twist, a really tragic irony.
Right. His work in public life, which in a way paid for his amazing science, also led to his death during the French Revolution. It's quite a story.
It really is.
So what are we covering? We'll look at how messy chemistry was back in the 18th century. We'll expose the, frankly, kind of funny flaws in the big theories back then.
Mm-hmm.
We'll see Lavoisier's super methodical approach and understand how his work still affects you, from the names of elements to just the idea of a chemical reaction. Okay, let's dive in.
Sounds good. It's pretty amazing to think how much we take for granted now. Back when Lavoisier was young, mid-1700s, chemistry wasn't really a proper science yet.
Right.
Still heavily influenced by ancient Greek ideas, Aristotle's 4 elements, earth, air, fire, water.
Jet classics.
Exactly. And then you had medieval alchemy adding its own layer of secret languages and symbols. It felt more like magic potions sometimes than actual study.
So total chaos for trying to share knowledge, I bet. Secret codes instead of clear formulas. Progress must have been incredibly slow.
Absolutely. And the main theory everyone kind of latched onto, trying to explain burning and rusting and all that, was George Ernst Stahl's phlogiston theory.
Ah, yes, phlogiston. Okay, so break that down for us. How did this theory supposedly work?
Well, Stahl, he was a German scientist, early 18th century. He proposed that basically anything that could burn contained this universal sort of fire-like stuff. He called it phlogiston.
Phlogiston, from Greek for flammable, right?
That's the one. And the theory caught on because it seemed to explain so much fairly simply.
And it sounds logical at first glance anyway. When something burns, poof, phlogiston goes into the air.
Right.
Burn charcoal, it gets lighter because it lost its phlogiston. Less ash means it had more phlogiston to begin with. Makes a certain kind of sense.
Yes, and it wasn't just for burning wood. It applied to metals, too. They thought metals also had phlogiston.
Okay.
So when you heated a metal and it turned into that powdery stuff we call an oxide now, but they call calx, they assumed it had lost its phlogiston. And if you wanted the metal back, you'd heat the calx with charcoal, which they thought was packed with phlogiston. The phlogiston would supposedly transfer back, restoring the metal.
Wow, it really covered a lot of ground.
It did. Even explained why a candle goes out in a jar. The air got saturated with phlogiston, couldn't take any more. Breathing, too. That was supposedly your body getting rid of phlogiston. So you can see why it was so appealing, this one idea explaining everything.
Okay, I get the appeal. It's neat. But despite everyone buying into it, there was this huge lurking problem with phlogiston theory, wasn't there?
Oh, absolutely. A fatal flaw, really.
Because while wood and stuff did lose weight when burned, metals did the opposite.
Exactly. Heat up lead in the air, and the calx it forms actually weighs more than the original lead.
More, not less.
Right, which completely blows up the idea that the metal lost something, lost phlogiston.
So that's a pretty massive contradiction. What did the phlogiston fans do? Did they say, oops, maybe this theory's wrong?
You'd think so. But no, it caused major headaches, but instead of ditching the theory, some just got creative.
Creative how?
Well, some suggested phlogiston must have negative weight, or levity.
Wait, negative weight? As in getting rid of it makes something heavier?
Uh-huh. That's the kind of intellectual gymnastics they went through, suggesting something gets heavier by losing a component just to keep the theory alive.
Wow. That really shows you something, doesn't it? Twisting logic to fit the story you already believe.
It really does. And it highlights perfectly why Lavoisier's approach was such a game changer.
He wasn't having any of that negative weight nonsense.
Not at all. He insisted that the balance, the scale, was the ultimate judge of what was true in chemistry. That focus on hard data, not just philosophical arguments, set him completely apart.
Enter Antoine-Laurent Lavoisier, born in Paris, 1743, studied law first, interestingly enough.
Yeah, but science was his real passion.
Yeah.
Kindled by a geologist, Jean-Étienne Guittard.
And he had this knack for really careful quantitative measurements early on. Got him into the Academy of Sciences super young, right? Like 25.
Remarkably young, yes. A real talent, clearly.
And his scientific work got a huge boost when he married Marie-Anne Pierret-Pauls in 1771.
A pivotal partnership. She was only 14 then, but became absolutely essential to his work.
Wow, 14. What did she do?
Oh, quite a lot. She learned English just so she could translate the work of British chemists like Joseph Priestley. She drew meticulous diagrams of his experiments, kept detailed lab notes. She was deeply involved. It shows how collaboration, even if not always formally recognized back then, drives science forward.
That's incredible. So this brings us to Lavoisier's core idea, his big innovation. This absolute insistence on precise quantitative measurements, using the chemical balance systematically.
Yes, that's what really transformed chemistry from this sort of qualitative art into a precise, quantifiable science. He was obsessed with accuracy, developed special equipment, even worked with Laplace on a calorimeter to measure heat changes.
I read he even stressed letting equipment cool down before weighing things to avoid errors. That level of detail.
Exactly. It seems obvious now, maybe, but it was a whole new way of thinking back then. It wasn't just about measuring. It was making measurement the final word.
The arbiter of truth, as you said.
Precisely. Shifting from relying on arguments or just noticing changes to demanding hard, quantifiable proof. That's the real revolution he started. Less about philosophy, more about data.
So around 1772, he turns this sharp quantitative focus onto combustion. Time to take on phlogiston head-on.
Yep. He experiments with things like phosphorus and sulfur, stuff that burns easily, and he shows, crucially, that they gain weight when they burn.
Gained weight because they combine with something from the air.
Correct. A direct punch against the phlogiston idea of losing mass.
But what was the something in the air? That was still fuzzy, right?
It was. But a key encounter helped clear things up. August 1774, Joseph Priestley, famous English scientist, meets Lavoisier in Paris.
Priestley. Another phlogiston guy, though, right?
Yeah, a big one. And Priestley tells Lavoisier about heating mercury oxide and getting this gas where a candle burned incredibly brightly.
And Priestley called it dephlogisticated air, meaning air without phlogiston?
Exactly. He thought its special properties came from being, pure air, free of phlogiston, so it could soak up more phlogiston from the candle or allow better breathing.
Amazing how they interpreted the same results so differently.
It really is. Lavoisier repeats Priestley's experiment, but through his quantitative lens, he sees something else entirely. He figures, okay, air isn't just one thing. It's got at least two parts.
One part that combines with the metal, supports breathing, supports burning.
Right, the active part. And another part that doesn't do those things, an asphyxiant part. By 1777, he's ready to drop his bombshell theory.
Which was?
Combustion isn't about releasing phlogiston. It's about a substance reacting with this eminently respirable part of the air.
Okay, so he's identified this key component. When does he give it a name?
A couple of years later, 1779, he announces it to the Royal Academy, calls this vital air oxygen.
Oxygen, from the Greek for acid generator.
Yes. He actually thought it was present in all acids, which turned out to be wrong, but the name stuck. Naming it was a powerful act in itself, staking a claim.
And he wasn't shy about taking on the old phlogiston theory directly.
Not at all. By 1783, he's launching this full-on assault, calls phlogiston imaginary, a veritable Proteus that changes its form every instant.
Wow, throwing down the gauntlet.
Absolutely. He said it was time to lead chemistry back to a stricter way of thinking, to separate fact from hypothesis. It was a real battle for the future of chemistry.
And his revolution kept going. Water was another big target, right? Still considered one of Aristotle's basic elements.
Yes, a huge one. An Englishman, Henry Cavendish, had isolated inflammable air, what we call hydrogen, back in 1766. He noticed water formed when you burned it in regular air.
But Cavendish explained that with phlogiston, too.
He did. But Lavoisier again saw it differently. In June 1783, he reacts his oxygen with this inflammable air and gets water in a very pure state. His conclusion, water isn't an element at all. It's a compound.
A compound of oxygen and this inflammable air, which he then named hydrogen.
Exactly. And he backed it up by splitting water back into oxygen and hydrogen. This was massive. If water wasn't an element, That really pulled the rug out from under the old system, and phlogiston lost another major pillar.
And all these super careful experiments weighing everything before and after. This led him to formalize a really fundamental principle, didn't it?
The law of conservation of mass, yes. He stated very clearly, in every operation, an equal quantity of matter exists both before and after the operation.
So burn that candle in a sealed jar, stuff changes form, but the total weight inside the jar stays exactly the same. Nothing's lost, nothing's gained overall.
Precisely. Matter is just rearranged. It's not created or destroyed in chemical reactions, this principle. It's everything. It makes chemistry predictive. You can calculate things.
Others had hinted at it before, right? Van Helmont, Jean Rey.
They had, yes. But Lavoisier's rigorous quantitative work, demonstrating it over and over, that's what cemented it as a fundamental law. It truly empowered chemistry as a predictive science.
Okay, so he's rewriting the rules of combustion, figuring out water, laying down the law of conservation of mass. But he realized the language of chemistry was also a huge mess.
A total mess.
Yeah.
Alchemical jargon, names based on how things looked or where they came from, like a secret code, as you said, made it almost impossible to communicate clearly or build on each other's work.
A science needs a clear language.
Absolutely. Lavoisier knew that. So in 1787, he teamed up with some other leading chemists, Gaëtan de Morveau, Berkeley, before Croix.
Right.
And they published the Méthode de nomenclature chimique, a new chemical naming system.
And the key was basing names on composition, right?
Exactly. So no more calx of zinc becomes zinc oxide. Tells you right away it's made of zinc and oxygen. Simple, clear, systematic.
It sounds technical, but it was also kind of a brilliant move strategically, wasn't it?
Yeah.
Oh, completely. By creating a new language built around his oxygen theory, he made his ideas much easier to understand and adopt. And it naturally made the old names tied to phlogiston seem obsolete. You still see that system's logic in every chemistry textbook today. It was revolutionary.
And then came his big textbook in 1789, Traité élémentaire de chimie.
Elements of chemistry, yeah. Huge influence. In it, he presented the first really modern-style list of chemical elements.
How did he define an element?
Very pragmatically. Basically, an element was anything that couldn't be broken down further by the chemical methods known at the time. The last limit of analysis, he called it.
So his list had things we recognize: oxygen, hydrogen, sulfur, carbon, metals.
Yes, lots of those. Though, reflecting the knowledge then, it also included things like light and caloric heat, which we now know aren't elements. But the approach was modern. The book basically laid out the whole new system of chemistry for everyone.
Amazing. But his life wasn't just science. He was deeply involved in public service, too.
Very much so. In 1775, he became a commissioner for the Royal Gunpowder and Saltpeter Administration, applied his chemistry to seriously improve French gunpowder production.
Making France more powerful, presumably.
Indeed. And his lab at the Paris Arsenal became this famous meeting place for scientists from all over Europe.
And he was involved in the metric system, too. That fits his love of order and standardization.
Totally. He was a key figure on the commission that recommended adopting the metric system in 1791. A rational, universal system, they called it. You see that same drive for clarity and logic in his public work as in his science.
But there's the other side. His wealth, the money that actually funded all this incredible, expensive research. Where did that come from?
Primarily from his role in the Ferme Générale, the General Farm.
The tax collection agency.
Exactly. It was a private company contracted by the monarchy to collect indirect taxes on salt, tobacco, things like that. And it was incredibly unpopular.
Seen as corrupt, part of the inequality of the old regime.
Deeply hated by many, yes. The tax farmers, the fermiers généraux, were seen as symbols of oppression.
And this is where the tragedy unfolds. His masterpiece textbook comes out in 1789.
The very year the Bastille falls, the start of the French Revolution.
And as things get more radical, heading into the Reign of Terror?
The former tax farmers became obvious targets. Being associated with the Ferme Générale was incredibly dangerous. Even Lavoisier's scientific fame couldn't protect him. People like Marat were publicly denouncing him.
So despite everything he'd given to science, to France, his past caught up with him.
Tragically, yes. May 8th, 1794. Arrested, tried, convicted as part of a conspiracy against the people of France.
And there's that story about him asking for a delay to finish an experiment.
On respiration, yes. A study that could have launched another new field. But his plea was rejected.
With that infamous line.
The Republic has no need of scientists. That afternoon, he was guillotined.
Devastating. Lagrange's quote about it taking an instant to cut off that head, but 100 years might not produce another like it. Just heartbreaking.
It truly is. A monumental loss, not just for France, but for the world.
So summing up Lavoisier, his story is just this powerful reminder, isn't it? How precise observation and just critical thinking can overturn centuries of accepted but flawed ideas.
Absolutely. He didn't just find new facts. He gave us a whole new way to do science. Chemistry transformed from, alchemy and speculation into a quantitative predictive science.
And his big contributions, conservation of mass, the oxygen theory, the naming system, they're still totally fundamental to how we understand chemistry today. You learn them in your first chemistry class.
And despite his awful end, his revolution happened quickly. Just like he thought, the younger chemist jumped on board. His focus on measurement, accuracy, clear language that became the bedrock for modern science paved the way for Davy, Dalton, Berzelius, all those giants who came after.
So when you think about Lavoisier, it's not just the amazing science, it's also this fragile balance, isn't it, between scientific progress and these unpredictable tides of society and politics.
That's a really important point. His life shows how even brilliant scientific minds aren't immune to the chaos of the world around them. The funding source enabled the science, but also led to his death.
It leaves you with a thought, doesn't it? What do we risk? What might we lose? Or maybe even gain? Though it's hard to see here when society pushes aside pure scientific inquiry, objective truth for short-term political goals.
That's the provocative question, isn't it? It's something that echoes way beyond Lavoisier's time, right into our world today, far outside the lab. Something definitely worth thinking about.